Let's talk about arena allocators in Odin. First, we'll look at just a simple example here, and then we'll look at some things where stuff maybe can go wrong or maybe not work like you expect. And then there are some funny sort of nuances that we can look at of how you can approach using them. So in this case, we have this little program here, and this program just allocates 1 megabyte of memory like this. This has nothing to do with the arena allocator yet. This is just 1 megabyte of memory. And then from the mem package in core mem, it makes a variable called arena, which is of type mem.arena, and then it initializes it here. And it feeds in this 1 megabyte block of memory. And this is the memory that this arena will use to allocate into. Or rather, the arena allocator, which we create here, will use this arena for allocation. So whenever this allocator is used, the allocations that is done through it will go into this sort of block of memory here. So here we dynamically allocate two integers, number 1 and number 2, and then we print some addresses here. So let's run this program and see what it prints. So it says arena memory starts at address, and then there's an address, and then it says number 1 is allocated as an address. And if you look at these two, it's actually the same. So this means that the first allocation ended up just at the beginning of the arena memory, which is maybe what you would expect. The second allocation, number 2, is at an address that is just, if you look at the address, it's just a tiny bit different. This is just actually 8 bytes later in the arena, in the memory of it. And that's because the arena allocates in sort of a linear fashion. By in a linear fashion, I mean that if the arena memory block looks like this, then the first number just ends up at the beginning, and then 8 bytes later, the second number can be, because it just like puts them in the order they are allocated. A thing to know about this arena allocator is that there is no such thing as individual deallocations. In order to free or deallocate the memory that is allocated here, you would run delete on this memory here. This just deallocates this slice of bytes, these 1 megabytes. That just destroys it. So for example, if we try to do what I call an individual deallocation, so like this, free number 1 and also pass in the correct allocator, because we must, when we free something, we must pass in the allocator that we use to dynamically allocate. Like I said, this delete here is what actually deallocates this arena. The arena allocator will not even implement this free. So if we did this and we run like we say free error, because this returns an optional error. So if you do this, then you will see it says mode not implemented here. And yeah, it's just that arena allocators do not implement individual frees. You can free everything in the arena in a few different ways depending on the arena, but you can, with none of the arenas in Odin, you can run free like this and assume it to do anything. And this is because arenas are, the purpose of them is to group things by lifetime. Things that you want to be deallocated at the same time, you can put into an arena so that you can just have one deallocation instead of several. Let's now look at a case where using an arena combined with a dynamic array goes a bit wrong, and I'll explain why this goes wrong. So if we look at this program here, just like the previous one, we start by allocating 1 megabyte of memory, and we create this basic arena. And I will get to some other arenas in a bit. This just uses the most basic arena that just you feed a block of memory and it allocates into that. But you have this initted like before, and then we print where that arena starts, and then we make the arena allocator. But then we create a dynamic array that uses that arena allocator, and then we append something to it, and then we append, and we print the address of it, and then we append almost 10,000 more things, and then we print the address of the first item again. Let's look at what this does when we run it. So it says arena starts at address blah blah blah, and you see that after one append, the first element has this address. So this is sort of expected. The arena starts, this address here is the address of the first byte in this memory, and after a single append, because the dynamic array doesn't have any data initially, but after a single append, it will grow once, and then it will get a internal capacity. A dynamic array has a capacity to store a number of items. When the capacity is full, it grows. So initially it has capacity 0, then it grows to get capacity 8, which is the default capacity. So that's what happens after this line. Now capacity is 8 after this line. And at that point, you see here that the first element is at the address of the first byte. Then when we do this thing where we append lots of times over and over, then the dynamic array will grow several times, right? Because first the capacity is 8, so when sort of you try to put in a 9th thing, it will need to grow, and then the capacity will become 24, and then it become a bit bigger, and it sort of grows geometrically like that. And so down here we see that the address of the first element is something else. It's no longer the beginning of the arena. So this is just something to keep in mind when you use arenas, like putting naively putting an arena allocator like this into as the backing allocator for a dynamic array is not always the best idea because of this. I have this illustration, and by the way, this illustration comes from a blog post that is linked in the description that talks about roughly the same stuff. And I have this illustration, and it shows how after one append, which is this case here, then it sort of looks like this. The arena, the dynamic array's data is like at the beginning of the, and this is maybe, you could think that this is the room for 8 elements here. And then after 9 appends, it has grown once more, and then the dynamic array's data is over here. Maybe this is room for 24 elements, but since you cannot do the individual deallocations, remember that's mode not implemented when you run 3 or try to individually deallocate anything in the arena. Since you can't do that, then this stuff back here, the old data, is just this dead area. It's sort of like if this arena grows several times, which it does in this case, then you will sort of have sort of a trail of dead stuff behind the current data block. So when you do it like this, your dynamic array will end up using more memory than it would if you just use the default allocator, which could do the individual deallocations. So let's talk a bit about a case where this actually behaves slightly differently than in the previous case with respect to how things get reallocated as it grows. We have changed which arena we use here. So here we use the virtual memory arena. It's the virtual growing arena we're using. So you import core mem virtual like this. I give it alias vmem, and I create the object like this, and then I initialize it. I say arena init growing. This is a arena that can grow as it runs out of space. It works by having blocks of memory, and when a block is full, it makes a new block and starts putting things into there instead. The old block will still be around. It doesn't resize any block. It just goes into the next block. This uses virtual memory. Virtual memory is a thing where the program you're running has access to the whole 64-bit virtual addressing space. So it can virtually reserve a lot of memory, and then it can commit it, as you say, in small chunks. When you reserve you can reserve 1 GB of memory, and your memory usage won't really go up. It's only when you commit it that it goes up. So what is quite smart, this thing, it just reserves a block, and then as allocations are actually coming in, it just commits it chunk by chunk, or rather it's called pages. So it maps this virtual memory to physical memory using pages, and it sort of expands like that. So it's quite a nifty thing, because it makes it possible to have something that grows without having to allocate a lot of memory for each block up front. You can just like reserve each block. And that also means that it can reserve quite a lot of memory, because the 64-bit address space is huge. It's a big number, but this one uses a default reserve space per block of 1 megabyte. So you can fill a whole megabyte of stuff, which is a lot for a array for you storing some structs or something. But it doesn't take 1 megabyte initially. It barely uses any memory at all initially when it's used like this. As we add things to it, it will use more and more. So it's very smart in that way, because since you have this reserved block of memory, your memory is continuous. The addresses are one next to the other because they are in they're next to each other in the virtual address space, which is what programs use these days to address memory. Anyways, so we create the arena allocator here, just like before, and then we feed that into the dynamic array here, and then we append one item and we say which memory address it has, and then we put in lots more, and then we do the same thing again. And let's see what this prints. So this one says after one append blah 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 this address, and then it says the same address, even though it grew 10,000 times. And here you might think like, but the other allocator couldn't do that. Why can this one do that? Why this dynamic array has grown from 0 to 8 capacity to 24 capacity, etc. And arenas usually don't support individual deallocations. Does this one somehow support individual deallocations? The answer is no, it does not. There is just a little special case in this arena that if the allocation you're trying to sort of reallocate is still the most recent one, it just reuses the same address. So this means that if any allocation happened in between here, say that you did like a new int arena alloc, let's just throw away that allocation like that. If you do this in between each, then you will see that this does indeed move, because in between each of these data blocks for the whole dynamic array, there is like a little int. There's lots of little ints, but they will sort of make it so that it can't just expand in place and make itself bigger. We can look at this picture again. I mean, what this virtual growing arena can do is if nothing has happened sort of after, if there's nothing after its current data here, then it can just make this thing a bit bigger instead. That's all it can do. But if something has ended up here, then it can't do that. So then it has to move the whole thing. So that's what we're seeing here. These two numbers are not the same because I added this line here. If I remove it, recompile, then they are the same. So that's something you need to know about this. The allocator in core mem, the one that we looked at before, does not have this behavior. I don't think there's anything technically stopping it from having it, so maybe it will get added in the future, and then my first example is sort of doesn't work anymore, or works better or something. But that's how it is. So what's this? Is this useful for something? Yes, because usually when you have a dynamic array and it grows, right? The whole data moves. All the data moves somewhere else. And that can be annoying if you have a pointer to some data, or you have, it can be lots of different things that are annoying about how the whole data block of a dynamic array moves to a new location. In this case, since it has a big block, it has a 1 megabyte block of memory for the growing arena, it can get up to 1 megabyte big. And that's the catch here. If this thing gets bigger, if this dynamic array gets bigger than the current block size of the dynamic array, then it will move, because then it needs to move to a new block, and that block will actually be make sure that there's enough space in that block to put in the big dynamic array. And I have an example of that too here. Here's the slightly modified example. So here I do the same thing, but I feed in 4,000 here to arena init growing. This is the default block size. So this is how many bytes should it reserve in the virtual address space. How much virtual memory should it reserve for each block? Essentially, how big is each block? So if we run this now, then you see that these two are no longer same, because this array will use more than 4,000 bytes of memory. The block it will need to move to eventually will actually become bigger than this, because this arena allocator here is a bit smart and tries to grow it when like uses more than 4,000 if it needs to, because the allocation needed to be bigger than 4,000. So here's a case where this doesn't work so well. However, I said before that you have the whole 64-bit addressing space for your virtual memory. So putting something like 4,000 here is silly, because you have such an enormous amount of addresses to use, and it's per, like, virtual memory is per program. So it's not like you're stealing some other program's virtual address space. No, you have your own for your program, so you only need to worry about that. So this number 4,000 here is silly. But if it is a concern, like even if it is a concern that you never want your dynamic array to jump to a new location in memory, you want it to stay at one location, what you could do is use a static virtual allocator. So let's look at that. Okay, here is the static one. The only thing I've changed there is changed arena init static. It still says 4,000. We'll change that soon to a more good value. But here we see that the difference between the static and the growing is the static has one block, and you say at the start, how big block do you want? So if we run this now, then there will be an error because it runs out of memory. See, append can return an error optionally here. And I check if what that one says, and it says out of memory down here. Now we see that because we imagine that we never want this array to move in memory. This could be useful if you have an array where you have handed out pointers and different parts of the program has pointers to it, and it's you want those to stay fixed for the whole execution of your program. So what you can do then is you can import, like if you want a bigger amount of memory available, you can import core mem again here, and then you can say like mem time like 10 times mem.megabyte or something like that. Then we have 10 megabytes, we run it, and then it's fine, and this has not moved because this has one giant 10 megabyte block. If you only have a few of these sort of big arrays in your program, using 10 meg, I mean, even if you have a lot of them, using 10 megabytes is fine. You have, I can't say the number because it's too big. I don't remember the number, the whole 64-bit addressing space, but it's a tiny part of how much you can reserve. You could put 10 gigabytes here if you wanted. It would still probably be fine. So this is a way to make a dynamic array that can grow, but it never moves in memory unless you put in 10 megabyte of stuff, which is a lot. If you want to learn more about manual memory management and Odin in general and arenas and all that, then I have written a book called Understanding the Odin Programming Language. You can go to odinbook.com and read a free sample. Thank you so much for watching. I'll see you next time. Bye bye.